So welcome everybody to our second Saturday Stars for November of 2018. I'm Monty Robson, the director of the observatory, and we're going to talk mainly about our meteor observation program. So we have three major programs of science and education. Asteroid observations that we started as soon as we had the observatory operational. Meteor observations since November of 2001. And meteorite studies since September of 2005. These three programs are things that we can do well. They're important to science. They're highly interconnected. They're very interdisciplinary, and they're exciting to students. So a large cosmic impact is at the same time the only known natural disaster that has the potential to end civilization as we know it. But it's also the only known natural disaster that we can think of ways to stop. No one knows how to stop a volcano, or an earthquake, or a hurricane, but we've got several ideas for stopping an asteroid impact. The whole idea is to find them before they find us. So we earned Observatory Code 932 from the Minor Planet Center in March of 2001 by reporting to the Minor Planet Center very accurate observations of the potentially hazardous asteroid 1620 Geographus. Since then we've made and reported over 2,300 very precise observations of asteroids and comets. We've always been in the top 10% of the world's observatories in terms of accuracy. We've discovered 4 asteroids. All have been numbered. 1 has been named. 2 are pending. We've confirmed about a dozen near-Earth asteroids and helped confirm more than 100. Meteorite studies began in September of 2,005 on a cloudy night. I wasn't down here, couldn't see anything, so I was at home and I was just browsing the internet for whatever reason, and here's what I found. This is an article from December 24th, 1807 from the Bridgeport Advertiser. Okay. I love the writing back then. They seem to be much more advanced than we are. I'll tell you what, they really do. On the morning of the 14th instant, what that means is of this month. Instant means of this month. About 6 o'clock, a terrestrial comet exploded nearly over the town of Weston. Well, that was nice, but what got my attention is right here. At New Milford, more than 20 miles from the point of explosion, the shaking of the houses was more severe than near the place of its discharge. So on December 14th at 6 o'clock in the morning of 1807, a meteor came down from up in the Albany area, over the Helderbergs, across the Hudson, came down right over top New Milford. At about 30 kilometers above New Milford, it fragmented, and with that, it really shook the houses. And for about 50 miles north of here also. So I said, wow, that's local history. That's something that maybe I can use to excite students. And so I started looking into it. The more I looked into it, the more I realized that almost everything that had been written about it was not true. So here's a map. It was published in scientific journal, peer-reviewed scientific journal, and this is the map that I made that showed where it actually fell. The red dots. This is the Eastern Reservoir. So none of the Western meteorite fell in Weston. Not a piece. But a lot of people don't know that. Anyway, so this was an aerial survey that I conducted in 2007. Then our first meteorite collection was donated to us in 2006. And it's seen much use, and it excites students. I'll tell you what, when you give a youngster a meteorite to hold and tell them that's the oldest thing they're ever going to touch, 4.5 billion years old, you know, it's a lot older than dinosaur bones. Anyway, our new collection was purchased in last June, and what it was the private collection of a long-time meteorite dealer. So it is fabulous, I'll tell you what. In it are over 220 localities, all types of meteorites from every place on Earth. Many of them are rare, many of them are historic, and they all have an interesting story to tell. So stay tuned. We'll give you a presentation like this on the collection in the near future. We're also planning to hold classes on them. So now for your vocabulary lesson. Meteoroid is a solid object in orbit about the Sun that is less than 1 meter in diameter, and it's been in space for billions of years. Larger objects are known, bigger than a meter, or they're called asteroids or comets. So a meteor, then, is the luminous track in the sky that we see, and other physical effects caused by when the meteoroid impacts the Earth's atmosphere at cosmic velocity. And they only last for a few seconds. And a meteorite are parts of meteoroids or asteroids that survive the atmospheric impact and are then found on Earth's surface. A fireball or bolide is a meteor brighter than Venus, which is about -4 magnitude. A superbolide is a meteor much brighter than the full moon, about -17 magnitude. They're very rare. Cosmic velocity, the minimum velocity that an object can hit the Earth, the minimum, is 11 kilometers per second. That's about 25,000 miles an hour, just a little bit more. But long period comets that are falling towards the Sun for a long time and accelerating, they can hit at over 150,000 miles an hour. So much faster than a speeding bullet. So our meteor observation programs began in November 2001 with the Leonid meteor storm, not shower. Every 33 years or thereabouts, the Leonids become very, very active as we fly through a debris field of them. And so they had predicted it for 2001. We had about 1,000 visitors here that night, and a good many of them spent the entire night here. About this time of year. It was, I think, the 12th or 13th, I don't recall, of November. We saw several thousand meteors. We had 2 or 3 different experiments going on. We gave a live radio interview of the event from here. and a meteorite collector in Connecticut, not collector, a dealer, loaned us for that event a collection of beautiful meteorites that had a retail value of close to $250,000. He trusted us with it. Anyway, parallax. The principle of parallax is a change in an object's apparent position when viewed from different locations. I'm sure a lot of you know about that. But by knowing the baseline, the distance between the two observing stations, and the angle, the difference in the angle of the object's apparent position, you can then calculate the distance to the object very easily. So if you don't know about parallax, you can experiment with it. So if you hold your finger up in front of your face, it doesn't have to be too close, okay, and then close one eye, and then look what's behind your finger, okay, then reverse it, open the other eye and close that eye, and you'll see your finger and go back and forth. You see your finger shifts back and forth. That's parallax, just the distance between your two eyes, the 3 or 4 inches between your two eyes. Now if you hold your arm or your finger way out and do it, you'll see it doesn't move as far. So the closer something is to you, the more parallax it will show. But that's what parallax is all about. So anyway, in 2002, a dear friend, Parker Moreland, Dr. Parker Moreland, who's outside someplace, I believe, and I set up an experiment. Now, scientists always have fun with making up names for things, so we called it Project Zombie to excite the kids, and that stood for Zenith-Oriented Meteor Baseline Imaging Experiment. Okay? I had to use a dictionary to find those, but so we called it Zombie. It was just a simple film camera with a normal 50mm lens. We should have used a wide angle, but we didn't. Mainly because this is the commonly used lens on a camera. And with a cable release, so we could expose the exposures for 14 minutes. Okay? But we had them arranged so they would point straight up to the zenith and north at the top of the frame. So we had a bubble level on this board and a compass and some leveling screws, and we put it down carefully and arranged it. So I did it from my house here in New Milford, and Dr. Moreland did it from Danbury, Connecticut. Now the reason for the different colors, we used different film. We didn't, I think we'd run out of the films we had. I used a Fuji film, and no, is that right? Yeah, I think I used Fuji, and I think he used Kodak. But there's 17 kilometers distance between my house and his house in Danbury. And so the same meteor for him, it started up north and ended right about here, well above Zeta Cygni. But here, the streak goes down and continues past Zeta Cygni. It shifted mostly to the north from Danbury because he's south of here. But from that, we both determined independently that that meteor ended at 100 kilometers in altitude, 62 miles. So how do we know it was a Perseid? Well, the Perseid, that was the peak of the Perseid meteor shower, August 11th. But also, here, this, if you're interested in astronomy, this is one of the best tools you can get. It's called Stellarium, S-T-E-L-L-A-R-I-U-M, Stellarium. And just Google that and you can download it for free. It is highly accurate. It gives you all sorts of ways to learn about it. But anyway, so how do we do? Look, there's the zenith where all the latitude and the meridians meet. Okay? And so it's just south of Deneb. Look, just south of Deneb. A little bit to the east of Seder, right in here. So that's where we wanted the center of the frame, and it looks like we did pretty good. Okay? So Parker's maybe a little bit closer because he's a little bit smarter. Although I got the looks. All my friends say I've got the perfect face for radio. Anyhow, but this shows you this Cygnids and this up here, the Perseids. That blue dot there by Perseids, that's the radiant. You'd be able to see the meteors going in any place of the sky. But if you take where they ended, in this case right around here, and trace it back, it will come to the radiant. So you might see one over here. If you trace it back to Perseus, then it's likely that it was a Perseid meteor. Okay, so here's a little bit closer. There's the zenith. That's where we wanted to have in the center of our frame. Deneb, which is Arabic for, I think, tail feathers. That's the tail feathers of Cygnus the swan. And Seder. And over here there's a bright one, but look, watch this. This bright star, and here's Deneb. And about halfway between and above them are two little ones here. So if we go back, look, Deneb, that other bright one, and the two above it. So I didn't say, but look. Why don't the stars look like stars? It's because we had a stationary camera. The camera was sitting on the ground, but the Earth's rotating to the east. So in a 14-minute exposure, the stars are going to trail, because that's a stationary camera on a rotating Earth. That gives you a star trail. Okay? Now, in August of 2013, we installed this, our first all-sky camera. Okay? And it's been imaging continuously since then. So 5 years and a few months, it's been imaging continuously. Look at this. This is image number 139, 139th image that camera had taken. And here's a Perseid. Here's, of course, the football field light. This is our satellite dish. Here's our weather station. When we first put it up, came in here and turned it on, couldn't see much because of all those parking lot lights to the east. So I quick found some cardboard and cut it out and went up and scotch taped it up over the camera so it would block those parking lot lights. Okay. So here was a meteor we caught in 2016 in March. Now we had an adult ed class that night. We've had an adult ed class on astronomy for every semester since we dedicated the place. And so here's a nice meteor. I don't know what that is. It could be a meteor, but it's more likely an airplane. But that's a meteor. Notice the image count, 1,106,761. It's taken a lot of images. Anyway, so a day or two after this, I got an email from the NASA All-Sky Network down in Huntsville, Alabama, and they wanted to know if we got that meteor. Well, I thought they meant that meteor. Phil Cloutier and I were giving a class that night, and we had all the students out on our outdoor observing deck, and we were pointing out the North Star and how do you recognize it? How do you find it? So it's halfway between this bent W of Cassiopeia and the Big Dipper. And these two stars at the end of the Dipper are called the pointers, and they point kind of in a direction, not exactly, but real close to the pole star, Polaris there, the North Star. So we were looking, all of us, all the students, and Bill and I, up at that star when this thing went by. So I quick ran in here and downloaded the image to the hard drive. They are already anyway, but I wanted to get it quick. But it turns out then after that we got cold, so we came back in. And about 55 minutes later, within an hour anyway, there was another bright meteor right in the same area. And this is the one NASA wanted to know about, not the other one, but I sent them information on both. But a few weeks before these two, here's what we saw. Look at that. That's a super bolide. Here's Jupiter. Okay, here's the Big Dipper up here. Here's the pole star. Let me show you something just quick for your astronomy education. Well, that's the North Star. That's not exactly at the North Celestial Pole, but it's real close. What I'm going to do is cycle back and forth through those last three pictures. And you watch. All of the stars are going to move, except that one. It might jiggle a little bit because all three of these pictures are maybe not perfectly aligned on the slide, but here, just keep your eye on it. See that? It doesn't move, but all the other stars do. Look, here's Orion down here. Look, over here, the next one, less than an hour later, it's over here. Anyway, that's the way it is, because we're rotating. So anyway, that super bolide happened on Valentine's Day morning of 2016. I don't know if you remember that morning, but I do. Not just because of the meteor, because it was the coldest it's been in the 30-some years that we've been in New Milford. It was 15 below that morning when I looked at the thermometer. It was cold. Anyway, this is a security camera in a guy's house, their home in Clinton Corners, New York, which is about an hour drive north of here, a little bit to the west. Here's Jupiter, okay? Let's see if I can put this into motion. Now here's what the super bolide looked like.
Wow.
Okay? Almost as bright as day. Anyway, the guy was...
What was the duration of that?
just about what you see here. Maybe 3 seconds, something on that order. We didn't count. I think it was about 3, maybe 4 seconds.
What was the big white blue thing?
What? What blue thing? Anyway,
That was kind of like...
this guy and his family were down wintering in Florida. And this company that makes the security things also links them up. They do all sorts of magic, but it links it up with your cell phone. So at about 4:30 in the morning, he got a call. Hey, something's happened at your house. So he's up and saying, oh no. And he went to the camera. You can also pull that from your cell phone. And he did, and he saw it was a meteorite. So then he posted it to the American Meteor Society. But, so anyway, those things do happen. So, our next step was this last winter. We were in discussions with the Sky Sentinel Network, and they sent us a camera. He told me it was one of their oldest cameras that they had in the network, and he was going to refurbish it for us. But look at what we're getting. So look, this was yesterday morning. 2, 3 from yesterday. Here's the day before. We got 4 of them. It was cloudy in between. Here's one on the 4th. Another 2 more, 3 on the 4th. Here's one on November 1st. So what we've learned with all this is meteorites, not meteorites, excuse me. I gave you the vocabulary lesson. I'm not saying it right. Meteors are a whole lot more common. The frequency of them is a lot more than any of us had ever thought. Okay. So they don't have any all-sky cameras in this part of the world. So Sky Sentinel put us in with the Pennsylvania people. This Keystone College is the only one that's really active. Rochester, New York is also sort of active. Keystone is about, oh, I don't know, an hour or so north of Scranton. It's almost exactly due west from here. So here is one that we got in July. This one up here on our original all-sky camera. And look, now it's 1,580,614 images. Okay. Here's what it looked like on Sky Sentinel. Okay, again, now there's only a few real things in this picture besides the meteor. But we got a video of it. See, the beauty of this camera is, the video camera, is that when it triggers an event, it gives you that last image that we just saw, which is a composite JPEG of the whole event. It takes all the images that had that meteor in it and stacks them together and puts it into one picture. But it also gives you a movie. Let's see if this one will work. Where's my, there it is. Okay. Okay, so it does work. That's what it looked like on the video camera. And this is what they call a PNG. It's about 500. It could be set for 1,000 now of the 1/30th of a frame of a second frame stacked together to bring out the stars. Well, it still doesn't bring out hardly any stars. Here's what Stellarium said was an all-sky picture that night. And so if you go back and do it, you'll see here's Mars. Here's Vega, maybe the 5th brightest star in the sky. Here's Arcturus, which is the 4th brightest star in the sky. That's all it gets. All the rest of these things, they look like stars or not. They're hot pixels. Here's one from just last week on Sky Sentinel. And here's from a new camera that we should have up shortly. It's a DSLR camera. Okay? We're going to zoom in on that. Look at the difference. Everything in here is a star. Here's Taurus the Bull. Here's the Pleiades. This is Capella. And look at that resolution. Really, really good resolution. And with that camera, we'll be able to see the end, the bottom of meteorite trajectories out to a radius of 600 kilometers from right here. So that covers all of New England except the northernmost part of Maine, most of the big cities in Canada and Ontario, out to the Pennsylvania-Ohio border, down into Virginia. From right here, we'll be able to see that whole territory. Now, you don't see it in there because that's in my backyard on the garden gate, on top of the garden gate. And so I got a lot of trees. One of the other files that the Sky Sentinel camera makes is a spreadsheet. But look, here's the time. Here's the 2018 10/31. So this was Halloween morning at 3:30 and 17.861 seconds. So this is giving you the time to the millisecond, which is important for figuring the velocity of it, which will give you the trajectory and then the orbit of it also. It gives you a lot of other data. This column here is the azimuth of the meteor, and this is the elevation of it. So it's a pretty sophisticated program. Now here's one we got yesterday morning. That's Sky Sentinel. Here's the DSLR.
What was the time on that?
This was at 5:54 and 31 seconds universal time. So it was just after midnight. It was, since we're daylight, we're not daylight saving time anymore, we're Eastern Standard Time. It was 54 minutes past midnight. So what was it here on the Sky Sentinel? 5:54 UTC, yeah. So the same time. Now, so which picture's better? Well, it's a silly question because the answer is they're different. They're both good. Sky Sentinel's given us the time of every frame to the millisecond. All I can tell you here is, as it stands now, this is a 30-second exposure. So the meteor happened sometime in the 30 seconds surrounding that time there. Oh no, that was the that was the start time of the image. So sometime from there to 30 seconds past is when the meteor happened. All right, but let's see, here was a close-up. So this image that I had been showing before, that's now discombobulated, but that live feed was from this camera here that was designed and built by an engineer who used to work for PerkinElmer, and before that had worked as a youngster for Grumman, making the lunar module. Mr. Peter Gagne, with help from another engineer, Jim Wood, designed and has built that camera, and the engineering in it is phenomenal. It's a video camera with a lens that has an auto iris in it, so if we get a really bright one like that super bolide, it won't overwhelm the image. The iris in the camera will close up, so it won't ruin the image. But look at that engineering. I'll tell you what, it is better by orders of magnitude than that Sky Sentinel camera. So it's up there operating now. Now, just a little bit of history. Look at the date on this. This is 1860. This guy here, Jonathan Lane, was quite a guy. He graduated Yale in 1846, and he wrote this paper. Let me just read you the title of it. This is 1860. Anyone know when photography was invented? Well, they were fooling around with it in 1827 in France. And a guy took a picture, one of the first pictures ever taken, of his garden in his backyard. It was an 8-hour exposure in 1827. So this is just a few years after that. Here's the title. On a mode of employing instantaneous photography as a means for the accurate determination of the path and velocity of a shooting star with a view to the determination of its orbit, by Jonathan H. Lane. So in this thing, he laid out what you needed to figure out meteor orbits with photography. A rotating shutter to be able to determine the velocity. Well, the video cameras, we don't need a rotating shutter because it's every 30th of a second. The need for a large field of view, a wide angle so you can cover the whole sky. And at least 2 observing stations so you can use the parallax and determine. See, in all the images that I've showed you from here, we can determine its approximate brightness, we can determine just when it happened, and we can determine the apparent position from here. That's not the true position. That's where it looks like it was from our perspective. You get another station or 2 or 3 other stations, and then you can triangulate it and know exactly where it was. The world's leader in this are the Czechs, and they can, with their cameras, which are DSLR based, they can determine at any point in that luminous trajectory the 3-dimensional position of that meteor within 15 meters. So that's our goal. Here is one of the first meteor images ever taken by a amateur, John Lewis, from Ansonia, January 13th, 1893. I don't know why they broke it up like this, but I guess to fit it on the page in the American Journal of Science. So Connecticut has a rich history and a bright future in meteor observations and meteorite studies. Thomas Clapp wrote it wasn't published. He wrote it before he died. It was published after he died in 1781. It was one of the first papers in the world on meteors. Weston, the first meteorite, it was that we discussed earlier, that was the first meteorite fall in the New World. Wait a minute, you say, you telling me that's the first one that ever fell here? That's not what I said. You have to know the definition of fall. If you're walking down the road and you say, oh, there's a stone, and you kick it, and you say, oh, that's an interesting looking, and it turns out to be a meteorite, that's called a find. If it's seen in the air, in the luminous trajectory, and then it's subsequently recovered, that's called a fall. So Weston was the first well-documented fall in the New World. Yale, their collection of meteorites was one of the biggest in the world in the early 1800s to the mid-1800s. A bunch of people at Yale, Newton, Olmsted, Loomis, a bunch of them were instrumental in confirming that meteor showers come from comets. And I showed you Jonathan Lane's picture his paper. And Yale began the first systematic program of meteor photography in America in 1893. The Czechs beat us by 10 or 15 years, but Yale was the first in this country, and they did have two stations. They had a Winchester Observatory in New Haven, and then in Hamden also. And then we began asteroid and meteor observations in 2001, and we're promoting an all-sky meteor network for Connecticut. So how can you participate? Shortly on our website, we're going to have up a meteor report form and instructions on what to look for. Because look, if you don't read that, you're not going to know what's important in the observations. What are the most important things you can tell us about what you saw? And how do you get that information? Well, so it's just a little one-page or maybe two-page thing on what you saw, and then there'll be a form on our website that you can report it to us, and then we'll let you know what our cameras saw and what we think of it. Anyway, if you're interested in anything I've said tonight, consider volunteering here. It's an all-volunteer outfit. We've got a lot of great people, men and women. And we also depend on donations and grants for all our funding. So any generosity would be greatly appreciated. Our future plans, we're thinking we will, depending on the weather, it's absolutely dependent on the weather, but the Geminid meteor shower is coming up, around the 14th of December. And that is one of the best, probably the best of the year, of this year. So we might see a lot of meteors, and we know where that's coming from an asteroid which they think is really a depleted comet. We're also going to hold meteorite classes and show everyone our brand new meteorite collection, which is just unbelievable. And then we want to establish an all-sky meteor program for Connecticut. So there have been 5 meteorites that have fallen in Connecticut. Weston was the first in 1807. In the last 44 years, there have been 4 more. So 1 every 11 years for the last 44 years. 2 of them landed in Wethersfield, but they both missed the Department of Motor Vehicles. So that's all I have, folks. We have a minute or two for questions.